Traditional text extraction is no longer enough for modern data. If you still rely on basic character recognition, your AI agents are falling behind. Older engines like Tesseract were designed for clean, linear print. They break when they encounter multi-column layouts, nested tables, or overlapping charts in real-world documents. The industry is moving to agentic OCR. These systems use spatial reasoning to understand a document's hierarchy, identifying headers, footnotes, and checkboxes before they ever attempt to read the text. This chart shows why the shift is happening. Legacy accuracy has flatlined, while vision language models, or VLMs, are seeing a massive spike in spatial reasoning capabilities. A vision language model processes both images and text simultaneously to understand visual context. But look at the secondary axis. Your GPU requirements are rising just as fast. You are now forced into a choice: route your private data through expensive vendor APIs, or build the heavy infrastructure needed to host these massive models yourself. We are going to look past the benchmark marketing to map specific model architectures directly to your throughput and budget constraints. Choosing the wrong approach creates a severe risk. When a model fails to understand a layout, it begins to hallucinate. This corrupted data feeds directly into your RAG pipeline, causing your AI agents to fail. RAG, or Retrieval Augmented Generation, is a system that grounds an AI's answers in your specific, retrieved documents. The most accessible path is the vendor API route. Models like Gemini 2.5 Pro and GPT-4o are built to handle complex, mixed layout documents immediately. You provide an image, and you receive highly accurate, structured JSON outputs backed by the reasoning capabilities of a frontier model. That convenience carries a heavy financial penalty. Processing at volume with these APIs can cost up to $15 for every 1,000 pages. Relying on external APIs also introduces latency. For real-time applications, waiting on a third-party server to parse a dense PDF will visibly slow down your user experience. There is also the issue of security. For healthcare or finance sectors, sending private documents to an outside vendor can break enterprise data privacy regulations. The vendor API route is a luxury tax. It provides immediate speed for prototyping, but it quickly becomes a financial and security liability as you scale. The alternative is the open-source VLM route. Models like Optical-OCR VL and Qwen 2.5 VL are designed specifically for local GPU deployment. Moving this in-house creates a massive economic shift. You get complete data privacy, and the variable cost drops to roughly 9 cents per 1,000 pages, a 167 times reduction compared to the APIs. This chart shows performance on OmniDocBench version 1.5. The red CanFan OCR bar reaches 93.1, outperforming standard pipeline models while keeping data on your servers. These models maintain performance across varied tasks. The top row shows high sustained scores for general text and multilingual datasets. The catch is the hardware. To achieve practical inference speeds, you must procure expensive, dedicated A100 GPUs. You also face significant engineering overhead. Deploying these models often requires precise prompt tuning to ensure they follow your formatting and don't hallucinate data. Open-source VLMs trade operational budget for engineering capital. For teams that can manage the hardware, it offers absolute control over the data and the profit margin. For teams processing at extreme scale, there is a high-throughput route. DeepSeek-OCR is the primary example of a model built for massive volume. It works through token compression. Token compression is a method of reducing the visual data an AI must process to understand an image. While standard models require over 6,000 tokens to read a page, DeepSeek-OCR uses only 100 visual tokens. This efficiency allows a single A100 GPU to process over 200,000 pages in a single day. At the opposite end of the spectrum is messy, unstructured data, like cursive handwriting and hand-marked forms. General OCR tools struggle here, often returning a word error rate of up to 95%. Word error rate is a standard metric that counts the percentage of missing, extra, or incorrect words in a transcription. For these documents, you need specialist tools, like handwriting OCR, which reaches a 0.9% error rate, or massive frontier models like GPT-5. High throughput and messy handwriting are the outer edges of OCR. One requires extreme efficiency, the other requires extreme reasoning. A middle-of-the-road tool fails at both. This chart provides a decision framework for 2026. On the horizontal axis, we plot implementation effort and compute requirements. On the vertical axis, we plot document complexity. Consider the app developer. You have low processing volume, but highly complex documents. For this profile, paying the API cost is the right move. It saves months of infrastructure time and guarantees the reasoning capability needed for messy inputs. Now consider the enterprise architect. You are processing millions of private, structured PDFs every month. In this case, capturing the 167 times economic shift of self-hosted GPUs is mandatory. For edge cases, your choices isolate further. If you need pure speed, run DeepSeek-OCR. If you need pure accuracy on handwriting, move to the top of the complexity axis with GPT-5 or handwriting OCR. There is no longer a single best model for every task. To succeed in 2026, you must match your specific document constraints to the right architectural workflow.